Just to start off with, I'm really sorry that I couldn't make it there today. I was at a conference, the Metabolomics Society conference last week, and I picked up COVID. So I'm at home recovering at the moment. So you have to, unfortunately, then hear me from home. So I'm going to lead on very nicely from what David spoke about today, and I'm going to take it through to, well, actually, can we use these molecules that we find in our food as biomarkers to tell us something about what people are eating? So what I'm going to cover are these food intake biomarkers, and I'm going to predominantly focus on the potential uses of these as opposed to how do we find these biomarkers, and then I'll end up with some take-home messages. So I'm interested in these food intake biomarkers like a lot of people, and there's been a great interest in recent years, and that stems really from the fact that we do have limitations associated with our current methods for assessing dietary intake. And I guess this audience is very well aware of all of these issues associated with self-reported intake mechanisms or tools such as food diaries, food frequency questionnaires, and 24-hour recalls. We know that there is recall of eating behavior, or difficulty in recall of eating behavior. We know that people often over-report foods that they perceive to be healthy and under-report foods that they perceive to be unhealthy. There are the issue around food diaries in that people will alter their eating habits because the very virtue of having to record what they're eating. So we do need more objective measures, and this is where biomarkers come into play. I will say from the outset that I don't believe that biomarkers will replace these self-reported methods, but actually I think the power or the benefit of combining both approaches will be really where we will get an increased accuracy of how we assess people's intake. So how do we actually find these biomarkers? I'm just going to go very quickly through an approach that we and others in the Foodball Consortium have used. We have used controlled interventions where we're intervening with individuals with exact intakes. We collect biological samples following the intake, and we look for biomarkers that are associated with the intake. We try to follow this up with validation and confirmation in different studies. So we often use dose response studies to see, well, if we increase the intake of the food, are we increasing the biomarker concentration? And then, of course, we try to move into independent studies to see if you have completely independent population and collection methods, do you still see an association between the intake of the food and the biomarker levels? So to just very quickly give you an example of that, I'm going to just briefly describe one study that we did through the Foodball Consortium, which was to look for biomarkers of legume intake and to try confirm some of these biomarkers. So we did a controlled intervention study where individuals consumed legumes, and in this instance we were interested in peas. They also consumed on different occasions different foods, which allowed us to use them as controls in our study. We collected urine following consumption of the legumes. We subjected this to metabolomic analysis, and then we identified metabolites or peaks that were increasing with the consumption of them, of the legumes. And these biomarkers then, they increase following consumption of the legumes, and then we assume that there are going to be potential or putative biomarkers related to food intake. So here is an example of some markers that change following consumption of legumes. So you can see very nice increase, whereas our control food, this particular biomarker remained completely flat right up to 24 hours post, 48 hours post consumption of the food. So you have three potential nice examples of biomarkers that are responding to this food intake. And here is an example of a biomarker that did respond, but actually so too did the control food. So we're less interested in biomarkers like this because they have a lack of specificity for the food that we're interested in. So once we had done that, then the next step for us was to try identify some of these features that were associated with the food intake. So we again performed ILSI MS to try identify these, went through databases to try see were any of these biomarkers in databases beforehand that would help us with the identification. And then where we could, we obtained authentic standards to validate the assignment of the markers. And the one I'm going to show you is 2-isopropyl malic acid. So when we had identified this marker, the next question was, well, if we increase the consumption of the legumes, do we increase the excretion of this marker in the urine? So in other words, is it responsive to an increased portion of intake? So we performed a small validation study where we had volunteers consume a low, medium and high portion of legumes over a period of a week. And at the end of the week, we collected a urine sample from these individuals. And if you look up here on the top right, you will see that as the portion of legumes increased, so too did the excretion of this particular biomarker. So what we had here was a biomarker that we showed in our acute study responded to legume intake. We showed in the confirmation study that if we increase the intake of legumes, we get an increased excretion of that particular biomarker. And the next thing we wanted to do was, well, see, could we validate that or could we confirm it in a completely independent study? So as part of Foodball, we were working with our colleagues in Lara Stragstedt in the University of Copenhagen, and they had completed a very similar intervention to our intervention where they'd actually used a pea burger as a control food. So we went back into their data set and we looked for our particular biomarker, and we in the individuals that consumed a pea burger, and we looked to see did it increase following consumption of the pea burger. And you can see here these are the different control foods that were used in his study. So you can see a very nice response again if this particular biomarker to consumption of peas. So what I've shown you here is a typical study that we would use and others would use to try identify these potential biomarkers that are associated with food intake. And there are many, many other examples of this in the literature, and I've just highlighted some of them here. And I highlight the systematic reviews that were conducted as part of the Foodball project. And as David said, they're all fully available online, and they're actually also available in a database. So what these tell us is that there are a lot of biomarkers associated with food intake, but predominantly what these systematic reviews concluded at the end, that actually very few of the biomarkers were validated for food intake. So that got us thinking in the Foodball Consortium to think about, well, how would you go about validating biomarkers for food intake? So we came up with a scheme that came up with some criteria that will help guide the scientists working in the area to look at different aspects of their biomarkers to see whether or not they're valid. So we came up with, well, is it actually plausible? Does it make sense that these markers are associated with food intake? Is there a time response to the consumption of the food, and what is the time response? Is there a dose response? So if the portion of intake increases, does the biomarker increase? What is the robustness of the data, and how reliable is the data? And then there are other things such as the analytical performance of the measurement of that particular biomarker and stability of the biomarker in question. So now we and others try, when we identify biomarkers, to validate them against these criteria, to try really push the field forward so that at the end of this work, we will have biomarkers that can be used by the wider community to increase our accuracy of dietary assessment. So what I want to talk about for the remainder of the talk really, and what I predominantly want to talk about was really how do we use these biomarkers. So there, as I said, there's been a lot of work done in trying to identify them, and very elegant studies identifying a lot of different types of biomarkers related to food intake. But I want to talk about, well, how do we actually use them, and can we drive forward the use of them? So if you think about these biomarkers, you can use them in many different ways. You can use them as a measure of adherence in nutrition intervention studies, and if we had a good set of biomarkers, this could really help us in our RCTs. We would ultimately like them to be a objective measure of dietary intake. We would like to combine them with our self-reported methods and correct the measurement error that we know that we have in self-reported data. And ultimately, these biomarkers can also be used to model the relationships between food intake and other environmental factors and health disease parameters. So I'm going to start now and just talk a little bit about a biomarker where we try to see whether we could actually get objective measures of dietary intake from that particular biomarker. So the concept behind this work was that you would take a urine sample, you would determine the biomarker level in that urine sample, and from that biomarker level, you'll be able to get an estimation of food intake. So to do this, we started working on a biomarker that David has mentioned already. That was a biomarker called proline betaine. So proline betaine has been well established in the literature to be a really good biomarker of citrus intake. So we were interested in measuring proline betaine in fasting samples and in 24-hour urine samples from a study. And we performed a controlled intervention study where we gave individuals different amounts of orange intake, and we looked at the excretion of the proline betaine in response to different amounts of proline of orange intake. Now, the idea then would be that you could take any urine sample, measure the proline betaine concentration, and then from that determine your orange or your citrus intake. So this is what we set out to do, but we also set out to compare it to our standard self-reported method. So we wanted to do it by our biomarker method, but we actually also said, well, let's compare it to what we would get with semi-weighed food diaries. So this would be representative of what we would have for our habitual intake in terms of grams per day. So we had two approaches, our biomarker approach, feeding into our feeding studies to get an estimation of intake, and we had our self-reported data from semi-weighed food diaries to get an estimation of habitual intake. To do the semi-weighed food diaries, we used a nationally representative sample from Ireland, which is called the NANS study. And what we took was the food diaries. We estimated citrus intake from that, and this is what we called reported citrus intake. We took a urine sample from these participants. We measured proline betaine in that urine sample. We plugged it into our equations from our feeding study, and we estimated or we predicted citrus intake in terms of grams per day. And ultimately what we wanted to do was to see, well, what is the agreement between what we predict from our urine samples with what we have in our self-reported data. Before I go on to show you that, I want to just take one step back to our controlled intervention study. And our controlled intervention study was large enough in that it had 50 individuals that we were able to develop the curves or the calibration curves based on 2/3 of the data and leave 1/3 of the data out. And the reason we done this was we wanted to test then on the 1/3 of the data, well, how good is the urine sample at estimating intake when we know the actual intake of the individuals. So what we did was we estimated the intake in these using the urine sample, which you can see over here on the right, and we compared that to actual orange juice intake because these individuals were actually housed in a metabolic unit and we knew exactly what they were eating. So you can see that there is good level of agreement across a range of different intakes between the actual orange juice intake and what we could estimate or predict from a urine sample. If we look at the correlation, you can see here again, this is a correlation between what we would estimate or predict and the actual intake. We have very high correlation values, both what is estimated from a 24-hour urine sample and what is estimated from a fasting urine sample. So how did it fare, or how did it work when we went into our cross-sectional study or our population study? So again, just to remind you, we took data from our urine data from our cross-section study. We plugged the concentrations into curves that we developed in a feeding study to estimate or predict citrus intake. And we compared this to our self-reported methods. And you can see here, this is a snapshot of the data. This is what's recorded in grams per day, and this is what we estimate from the urine sample. And again, across a range of intakes, we get very good agreement across a range of different intakes. If you look at the whole 600 individuals, we see that on average, the mean difference, you can see it here, is very low, but actually there are individuals where there is large disagreement. And if you think about it, we would expect this because we would expect that certain individuals will have misreported their intake, and therefore we would expect that we would have a certain portion of individuals where there is a difference in what they're reporting and what we're estimating from the urine sample. But on average, we can see that there is good agreement between the two methods, and that the urine sample done pretty well at estimating citrus intake. So then that brings us on then, well, where do we use this, and how can we move this into more larger epidemiological studies? And do we actually need to measure the biomarkers in all of those studies, or on all of those samples? And I think we don't. I think that we can start to use our self-reported data, and that we can model the relationship between our biomarker data, our self-reported data, and then correct a large portion of the self-reported data in the population study. So the concept behind this is that you have your biomarker data, you have your self-reported data, you model the relationship between these two in terms of calibration equations, and you use the estimates from these calibration equations to correct the self-reported data in a larger sample size. So we tried this out again in the case of proline betaine for estimating citrus intake in a population study. So the concept, again, just to reiterate, is that you model in these calibration equations the relationship between the biomarker estimated citrus intake and the mean daily self-reported intake, and you take the estimates from these, and you develop your calibrated mean daily citrus intake. So we did this on 800 individuals, and we got, you can see the results here. This on the black is the self-reported data, and then on the grey is the predicted that you would estimate if you use 600 of the individuals to develop the calibration equations and you correct your self-reported data. And we've developed an online app that you can do this, and all the data is that app is freely available for people to have a look at and to play with. So this is a very nice example of how you can model both biomarker data and self-reported data, and then you can use it in a larger portion of the population group. But how much biomarker data do you need to do that? Well, we carried out a number of simulation studies to try address that question in terms of the proline betaine biomarker. And you can see here that you get a rapid stabilization of the estimates when you have about 20 to 30% of the population with biomarker data. And that means that adding extra biomarker data isn't helping in any way in the models. So for this particular biomarker, we estimated that you need between 20 and 30% of the population to have biomarker data. You model the relationships, and then you can correct the rest of the self-reported data for measurement error. So again, this is something I think that we need to develop further. We need to look into this further for other foods and other biomarkers, and I think it has a great potential in helping us correct some of the issues that we have with self-reported data, and it really is trying to combine both sets of data. Then if we think about it, and again, this is what's emerged in the literature, is that there's very rarely going to be one biomarker for one food, and the proline betaine is an example of one biomarker for one particular food, but it's actually probably one of the few examples of that. And what's emerging is that people are more and more talking about biomarker panels. And what these are combination of biomarkers that together give you a better estimate of that particular food. And that means that you can have a whole range of different biomarkers that are telling you maybe something slightly different about the food intake. But by combining them together, you're getting a more holistic view. However, when you do that, you need to have new statistical tools, and modeling can be quite difficult in that instance. So we developed a framework called the multi-marker framework, which allows you to model multiple biomarkers against a continuous intake, with the idea then that you could take multiple biomarkers and get an estimate for that particular intake. And what was very nice about this work is that we also done it in a Bayesian framework, so that you could get 95% confidence intervals around your estimation. So you could have an uncertainty around that estimation that you were building from your biomarker data. We've developed an app, again, this is freely available, that allows individuals to do that. So the concept being that you have your multiple biomarkers, you model your multiple biomarkers against your continuous intake, and then from that you get your model estimation, and you can pull that into when you have biomarker data only, and you can get an estimation of the food intake, and you can also have an uncertainty around that estimation. So then for the last part of the talk, I want to talk about dietary patterns, because this again is something that's emerging in the literature, that while we can be very focused on particular foods, but actually it's the total dietary pattern that's really important. And potentially biomarkers and panels of biomarkers and combinations of panels of biomarkers could really help us in this case. So a few years ago, we were interested in this, and we were interested in developing a metabolomic-based classification system for classifying individuals into different dietary patterns. So we built a very crude one based on the metabolomic profile, where we could classify an individual into either a healthy dietary pattern or an unhealthy dietary pattern. So more recently, we have followed this up, and we have developed this further, and now we can classify individuals into 4 different dietary patterns: a moderately unhealthy, a convenience dietary pattern, a moderately healthy dietary pattern, and a prudent dietary pattern. So we built this model in a nationally representative cohort of the Irish population, and then we tried to validate this or confirm it in an independent study. So in our independent study, then we had 4 different time points, so repeated measures of the urine data and the food diary data. And what we found here is that we actually could replicate, number 1, the 4 dietary patterns. But actually what was really interesting was that we could see whether these 4 dietary patterns were reproducible over a very short period of time. So this was once a month over 4 months. And you can see that reproducibility here in these spider diagrams. So here you have the moderately unhealthy dietary pattern, and here you have the convenience dietary pattern. And what you can see here is that the individuals were tracking, the dietary pattern tracked very nicely across the 4 different time points. And bear in mind that this dietary pattern was classified due to a metabolomic pattern, and then confirmed later with the dietary data. And you can see again here for the convenience dietary pattern that it was extremely reproducible as well. So I think this whole area of dietary patterns is an area that warrants further investigation. It's an area that potentially biomarkers could play a huge role in trying to classify individuals into different dietary patterns, and then potentially also combining the self-reported data in that context. So what I've spoke about so far today is really trying to use biomarkers to tell us about food intake. But actually, not all biomarkers are going to have a relationship with just food intake. Some of the biomarkers are going to be influenced by the microbiome, and some biomarkers are going to be influenced by genetics. And that doesn't mean that those biomarkers are not particularly useful in any means or form. It just means that we might use them in a slightly different way. But either way, these biomarkers, as long as we acknowledge what they are being influenced by and acknowledge the complexity of some of these biomarkers, we can then go on and use them to study health parameters, look at disease risk factors, and maybe potentially also some disease outcome measurements. And we're starting to see more and more of that, where we know that the biomarker levels are modulated by food intake, but we also acknowledge that there are other factors in modulating these biomarker levels. It makes it more complex, but I think that's the way we have to think about it, and that's more research is going to need to be done to try disentangle some of these factors that are influencing these biomarkers. So then, just to conclude, I hope I've shown you that we can get useful information from biomarkers about what we eat. Biomarkers can be used to in the case of proline betaine, to estimate intake, and it compared very well with habitual 4-day records. Biomarkers have the potential for classifying people into different dietary patterns, and I think this is an area that needs to be further developed. And really potential for combining our data and our biomarker data with self-reported data is a huge area that warrants further investigation. However, there are lots of challenges, like anything. David alluded to it, and I think some of the work that his group are doing can help immensely with this, is that unassigned features in the profiles is a huge issue in terms of biomarkers of food intake, because many of the current databases just don't have those biomarkers. We're interested in those. We do need international alignment to try and improve this and to try and improve the annotation of our metabolomic profiles. Many of the biomarkers that are related to food intake are still not validated, and validation efforts are needed. And then the role of dietary patterns and the potential of biomarkers in dietary patterns is an area really that's only starting to emerge at the moment. And there are lots of other questions that we need to ask. Well, how many repeated measures should we take so that we get a good representation of habitual diet? And are there different ways, and exploring different ways of combining our data with dietary data? So just to end up with a take-home message, I hope that you can see that we do have useful information in these metabolites. They can give us information on food intake, and that we do need international efforts to try help us improve our feature identification in our metabolomic profiles. Finally, then, I'd just like to thank all of the members of the team in UCD, all of the collaborators that we work with across various different projects in Europe, and our funding agencies for funding this work. And thank you very much for listening.
Thank you, Lorraine. Do we have questions over there?
So, nice talk. Thank you. My question is a double question. Probably one of the most important parameters in all your work is the sensitivity of the chemical analysis. So I would like to know if you have developed some methodologies or whatever to overcome this problem or to improve this, that for sure will allow you to find new biomarkers at very low concentration. And the second question is why always urine? So did you consider to find biomarkers in serum, plasma, etc.?
Oh, yes, okay, so I will start with the second question, the second part of that question. So what I presented today was only urine. You're absolutely correct. We have worked with plasma before, and we continue to work with plasma. So for certain foods and certain biomarkers, plasma will be really good and will be really useful. It's just so happened that what I pulled together today was based on the urine data, but we do work also with plasma. And then the first part of your question was about sensitivity, and if we've developed any methods to overcome that. Well, I leave that to the instrument developers. So they're also always developing new instruments and technology to get more and more sensitive assessment of biomarker of the metabolites that are present in samples. But the sensitivity across it has improved hugely, and of course LCMS is more sensitive than NMR, but you can do things with NMR to improve its sensitivity as well.